And good evening, AP Physics student. Mr. Kirsten coming at you here, talking about average kinetic energy of an ideal gas today. Today's formula that we're going to use in problem 47 looks like a rather simple one, but it's really kind of mind-blowing how simple it is and yet how we can derive it. Here's what the equation says. The equation says for an ideal gas, the average kinetic energy of one molecule or one atom of the gas is simply equal to 3/2 times Boltzmann's constant times the temperature in Kelvin. Okay? Keep in mind, temperature has to be in Kelvin, right? And Boltzmann's constant, you guys know now, is 1.38 times 10 to the minus 23rd joules per Kelvin. Now, this, when you think about it, is a really simple equation. I mean, it's complicated how many atoms there must be bouncing around in a mole of gas, say, at standard temperature and pressure. But this equation is derived in your book on page 368 to 370. And we don't have time to look at it here in a 10-minute video, but what's neat about the derivation is it only uses classical mechanics. Things like force and momentum and changes in velocity. Things that you guys are very familiar with from your study of mechanics first trimester. So it's really a pretty cool derivation that we can figure out the average kinetic energy of one molecule of an ideal gas simply by knowing its Kelvin temperature. Okay? So if you were to double the Kelvin temperature of a gas, you would double the kinetic energy of its particles. So temperature really is a measure of the kinetic energy of the particles in an ideal gas. Okay, well, what else can we derive from this equation then? Well, if this is the average kinetic energy of a gas particle, okay, one other thing we could say is 1/2 mv squared, where v is kind of the average, would have to be equal to 3/2 kT. Now here, v is the average speed of a ideal gas particle at a certain temperature. So we have a special name for that. We call it the root mean square speed. So fancy, and if you've taken statistics, you know exactly what that means. But anyway, we could solve for this. If we solve for this v, we call it the root mean square v, right? We would take this equation and the 1/2 would cancel, and we would simply have 3 kT divided by m, where m here is the mass in kilograms of one particle. So it's usually measured in AMUs, although AMU is converted into kilograms. All right. I always think this is a pretty amazing result that you can actually, just by knowing the temperature of something, for instance, right now it's about 0 Celsius outside, or 273 Kelvin. You can calculate how fast the average air molecule is moving just by knowing the temperature. Anyway, I always thought that was pretty cool. But enough about this. Let's get to our problem number 47, which states calculate the average speed, or root mean squared speed, of the average helium molecule that's floating around the sun. And we're told here that the temperature of the sun is about 6,000 Kelvin in the outer part of the sun. So we are going to calculate this speed by using our equation here, which, by the way, this equation is on your equation sheet, so you don't have to memorize it, at least on the free response part of the AP test. So that's equal to the square root of 3kT divided by m. So for helium here in the sun, we would do 3 times 1.38 times 10 to the minus 23rd times our temperature in the sun, which is 6,000 Kelvin, divided by the mass of one helium atom. And that mass is approximately 4 AMUs. So that would be 4 times 1.66 times 10 to the minus 27th. So if we plug all of that into our calculator, we should get an answer that looks something like this. This is 6,100 meters per second. So the average helium atom near the surface of the sun is traveling at 6,100 meters per second, which is kind of cool that we can figure that out when you think about it. You know, figuring out how fast an atom in the sun is traveling is, I don't know, that's pretty neat. When mom or dad ask you what you did in school today, just say, oh, not much. I just calculated the average speed of a helium atom moving around the sun, you know, in the sun. So anyway, pretty cool stuff. Other cool stuff, man, I just love science, and there's so much cool stuff going around. Did you guys know that 130 million years ago, birds actually had 4 wings instead of 2? Holy cow, look at all this cool science that is around. All right. This is from Sunday's Star Tribune. You should check out this article if you're at all interested in birds or dinosaurs or how one may or may not have turned into the other. Really, really cool stuff. All right, nice work, AP Physics students. We will see you tomorrow.